If our matrix has m rows and n columns, the null space organizes all vectors with n coordinates that satisfy the equation A times r vector equals the 0 vector. Today we'll introduce a new type of subspace that we attach to a matrix called the column space of a matrix. So what is the column space of a matrix? Well, if our matrix is m by n, the column space is denoted with the notation col of A, and this is the collection of all vectors v and rm, so here m is the number of rows, that satisfy the equation rank of A equals rank of A augmented with v. So this is different from the null space. The null space collects certain kinds of vectors that live in R to the number of columns. The column space organizes vectors that live in R to the number of rows. To live in the null space, you have to satisfy the equation A times the vector equals 0. And to live in the column space, we need to satisfy the equation rank of A equals the rank of A augmented with the vector. So let's see an example here. So here, again, when we write that V belongs to the column space of A, what we're doing is we're communicating that the rank of A is the same as the rank of A augmented with V. So in this example here, what we're doing is we're taking a matrix A and we're augmenting with a vector V. The matrix A that we're interested in here is 4 by 3, and we're augmenting with a vector V that has 4 entries in it. 1, -1, 83, 8. Now I row reduced this augmented matrix, and I got this matrix on the right, and we see here that on the right we have 3 pivots, but they're all to the left of the augmented column. So there's no pivot in the augmented column when we row reduce. So this means that the rank of A itself is the same as the rank of A augmented with V. This is the same thing as saying that the V we're working with here belongs to the column space of A. Let's look at a different example. We have the same coefficient matrix here, A, and we're augmenting with a new vector. Maybe let's call that vector W. When we do the row reductions after augmenting, we have our 3 original pivots to the left of the augment, but we also have a pivot in the augmented column. This tells us that the vector W we're working with here does not belong to the column space of A. So in order to belong to the column space of A, you need to, or if you are given a vector and you want to test whether or not that vector belongs to the column space of A, you augment A with the vector in question, and you row reduce, and you look for a pivot in the augmented column. So think about where we've seen this before. Where have we seen the equation rank of A equals rank of A augmented with something? This is the Roach-Capelli theorem. And the Roach-Capelli theorem says that a pivot pops up in the augmented column exactly when the associated system of equations is inconsistent. So one way to think about the vectors V that live in the column space of A is that the V that live in the column space of A are exactly the V that make the system AX equals V consistent. So here we have a different example. We have a 4 by 3 matrix A, and here we're augmenting with this vector V, which has coordinates 2, 4, -2, 0. Again, A here is 4 by 3, and the V we're looking at might live in the column space. And the reason we know it might live in the column space is that it has 4 coordinates. But when I do my reductions here, I end up with 2 pivots to the left of the augmented column and a pivot in the augmented column. This tells me that the system I'm studying is inconsistent. So the vector V that I'm looking at here does not live in the column space of A. Here's a different example. So we have the same coefficient matrix A. Again, this one is 4 by 3. And here we're augmenting with the vector -1, 0, -1, -4. Let's call that vector W. When we do the augmentation and take the row reductions, we end up with a reduced row echelon form, and the pivots are not in the augmented column. So we end up with a consistent system here, which tells us that the W we're studying does belong to the column space of A. Great. So again, to test whether or not a vector is in the column space, augment your matrix with that vector and check whether or not that system is consistent or not. Now, think for a moment here about how this differs quite a bit from the idea of a null space. If I give you a vector and I ask you, is this vector in the null space of a matrix? That job is actually not very difficult. You just multiply your matrix by the vector and you verify whether or not you get 0. But if I give you a vector and I ask you, is it in the column space? That problem's a little bit more difficult because you have to do row reductions in order to solve the problem, and row reductions take some time. On the other hand, if I give you a matrix and ask you to give me examples of vectors that live in the null space, that's a difficult problem because you need to row reduce the matrix and describe all of the solutions to AX equals the 0 vector. On the other hand here, if you just want to produce examples of vectors that live in the column space of a matrix, rather than verify a given vector living in the column space, all you have to do is multiply your matrix by some vector of coefficients, and that produces something new in the column space. So for example, let's take our 4x3 matrix A and multiply by the vector 1, negative 3, 2. That produces the vector 6, negative 5, 0, negative 16. And that vector has to live in the column space because I know that A times X equals this vector is consistent because one of the solutions is 1, negative 3, 2. Let's take the same matrix and multiply by a different vector, negative 2, 5, 1. That produces 22, negative 5, 14, 28. I know this vector has to live in the column space of A because A times some vector equals that vector. Remember, inconsistent means there is no X that solves the equation. So the fact that we're providing some vector we can multiply by to produce these two vectors on the right here means these two vectors on the right are in the column space. So this gives us maybe a more concrete way of thinking about what the column space consists of. The vectors that live in the column space of a matrix are exactly those that can be expressed as linear combinations of the columns of A.